Thank you. Hello. I'm proud to present this project. As mentioned, my name is Eike Gassen, and I will present you the project in autonomous lightweight robot in steep slope viticulture. I will start with the levels. I will give a short introduction or motivation of what is steep slope viticulture and how it's different in terms of the standard and normal viticulture in Germany. I will give an overview over our design of the robot. I will give a short overlook over our simulation of the robot and the Vineyard environment. I will very shortly introduce our control architecture, and after that I will give a concept optimization idea and so with outlook of further steps. So what is a steep slope vineyard? Here I have two pictures comparing the steep slope on the left side. This is my hometown, which is built, as you may see, in a very steep terrain. These are inclinations up to 80–90%. Here about 100%. And in comparison to that, there is a flat terrain vineyard from USA Napa Valley. And I think it's relatively obvious that there is a different amount of work to be done in the left picture compared to the right picture. Therefore, I will shortly introduce the steep slope cultivation itself. In this steep slope cultivation, you have this so-called hull line cultivation. That means the vines are planted in direction to the slope, and because of the high inclination, it's not possible to do this with a normal standard tractor which drives in the horizontal vineyards. This means you have a much higher amount of work, manual labor, and in Germany we have the situation that we have a shortage of workers, and the only possibility to still solve the work in these vineyards is to use autonomous robots. Here a short overview of the costs which we are facing in viticulture. The different colors are describing here on the left side. The labor cost is, for example, this blue one here, comparing ordinary tractor work in the flat terrain, ordinary tractor in steeper slope, and here we are in the handwork part, where we see that the labor cost in viticulture is more than 3 times as high as in the flat terrain vineyards, which is also an argument why to automate it, because obviously we want to decrease the costs of the labor. And here on the right side, also you see the some different tasks we have to do. Here, for example, is the plant protection, so spraying agent application, for example, and the gray part is handwork, and you see that it is compared to tractor, which is the red one, really a huge amount of factor 15, increasing this handwork. And because of that, especially the application of spraying agent is one of the most important parts which we have researched. So overall, the idea is to reduce costs for the farmer and increase the health of him because of not applying the dangerous, hazardous spraying agent. Now here are the requirements for the vehicle itself. We said that the vehicle should be able to drive in vineyard which have a length of 100 meters. and if the vehicle should be possible to solve inclinations up to 70%. Also, here are a few dimensions of it, which it has to fit because of already existing vineyards. For example, the width is important because of the difference between the vines. It has not be wider than 0.8 meter. The height is important for transporting the vehicle itself from vineyard A to vineyard B with a tractor or a truck itself. And because of that, if it would be too high, it would not be possible to transport it in an easy way. And also the speed is important. Of course, we try to work as fast as possible, but on the other hand, we want to have a long time of working without changing accus. So we want to have a good mixture of mass and mass should be as low as possible and speed as high as possible. And so these are the requirements we set. And because of the 70% inclination, it is necessary that we using a winch, because otherwise we are not able to solve this slope. And also because of safety, we need this winch. And here I have the concept of this truck-trailer combination. Here, this part is the robot. This robot is transported by a trailer, which is rotatable for 90 degrees. Then we can drive downwards and upwards. And in each step, downwards drive as well as upwards drive, we are able to work doing applications and to do different stuff. And if we drive up again, we drive back to the trailer, and with the tractor, we drive to the next row. And then everything repeats. And so we are working in the whole steep slope area. So driving from one row to the other, going down, up again, and this for the whole vineyard. This is the idea of how we working in this steep slope area. To introduce the different possibilities of the kinematics of the robot, I will show you the different possibilities we have compared with each other. We are starting with Ackermann kinematics, which we researched with 4-wheel drive and 2-wheel drive. Also, we thought about tricycle, which was rear and front wheel driven, and also a differential steering with these 4 different possibilities with caster wheels. And also we have skid steering, also with tracks, and a 6-wheel skid steering. And we had this articulated steering, so-called, with 2-wheel drive and 4-wheel drive, which has this bearing here in the middle, which also makes the steering easier and more accurate. And now I will show how we discussed or weighted this different concepts. Yeah, here is just an example of 2 of the compared kinematics. And we thought about how to evaluate these concepts, which criteria are there, which we can compare, and which criteria are really important. And as I said, the weight is of really high importance because we want to make a robot which works as long as possible with the accus on it. And obviously, if you have to move more mass upwards and downwards, you need more energy. And if you need more energy, the accu will last not so long as if it would be lightweight at the construction. Also different point which we took a look at is the spatial arrangement on the vehicle itself. So which influence has the kinematic concept of the possibilities of mass distribution, and also mobility, the ground contact, and the stability against tilting is also, of course, really important, because in the inclination we still don't want that the robot tilts neither lateral nor backwards, and also the controllability is of much importance, because we want also in this rough terrain a robot which is able to drive in the way we want it to. And now I show you the way I modeled the different concepts. We started with a point mass model. So here are the different parts we have mounted. For example, this is a spraying tower, as I said, for a spraying agent application. And we looked up the center of gravity of all the different components. Here, for example, are the batteries, and here are the computers, the tank, and all these different parts have, of course, center of gravities. And we compared this resulting different centers of gravity, and compared the different possibilities. And the aim, of course, is to have as low as possible center of gravity, which should be as front graded as possible. And because of that, we made different models. We made different models of the kinematic concepts, and find in that way a possibility to compare them against each other. This is in general the concept how the robot, the easy model, is built up. In front is a winch. There is a force which pulls the autonomous robot up and down the slope. And here are the wheels or chains or whatever the concept is about. And you have this tilting against, so backwards tilting, that means the robot would fall back. And you have also this sidewards tilting, because the line itself could also be tilted to the sides. So we considered the side and backward tilting and calculated the maximum angle when tilting starts. And yes, this different concepts we compared in a cost utility analysis that worked in that way, that we had this criteria, and these criteria were weighted. That means more important criteria like weight, like the weight, has a factor of 0.2. Not so important factor like the not so important criteria like spatial arrangement, and it has just a weighting of 0.05. And as you may have noticed, the sum of all the weightings is 1, and so you have the possibility to weight the more important criteria. This we have done for every of the 16 shown concepts, and this is just a short excerpt. And with this, we decided which concept is the most appropriate to really build. So, and in parallel, we start simulating all the stuff. Like Professor Burns introduced, there are a lot of reasons why we are simulating, and here are a few examples of our simulation. For example, light conditions, and we are able to also simulate the weather, like snow, wind, and dust, and all these things, which we, of course, were not able to take a look at if we not have really already built up robot. So we start in parallel with the simulation, and here we have the two short videos of the simulation, where you can see we have here the grades and the so the rough environment. And in the upper right picture, you see the really first rough kinematic concept of the tractor. And yes, then we started with building up a prototype. This prototype, we also, and at this prototype, we also added in front and take the ZTV camera for path tracking. And here you see the steel cable of the winch. We have here the differential drive, which we use to steer and propulse the vehicle. So we are able to turn with different speeds of the different wheels, and also can additionally propulse the vehicle up and downwards. We have here also a GPS and an IMU which delivers the tilting of the vehicle, which we need because we have the different tilting angles. We should not pass, because otherwise the vehicle would tilt. And with this, here are a few data where the vehicle has which sensor mounted. We can discuss it afterwards if needed. And here I will show you a short video of a record in the Vineyard. And yes, here you see, here on the upper left, you see a point cloud of a LiDAR sensor, which has sensor fusion with the left and right camera of the vehicle, and here the front camera of the vehicle itself. The front camera you see here in the upper right image, and in the middle left and right image you see the foliage and the grapes of the vineyard itself, and beneath that you see the OpenStreetMap, so the GPS signal, and here you see a 2.5 GD graphic of the surface the robot is driving. And here on the left side you see a bitmap where the rows are in red, where the lines of wine are planted in red, and the green parts where the robot is able to drive. And here you have also a model of the robot. And after this, here you see the different vines. I don't know if you can see it that well, which are recognized from the algorithm. This we use to make a short rough estimation of the yield. This records, and yeah, now I will shortly give an overview of the needed properties of the architecture of the robot. Of course, it should be modular, extensible, and maintainable, because the robot is meant for supporting the farmer over the whole year. So modularity means in that way that you can add different attachments for support the farmer in different working steps. Obviously, the robot itself has to be robust against weather, illumination, and season-related appearances like falling leaves and all these different things which appear in agriculture. And we have to be able to perform in real time, because we have to adapt to different concerning problems which can appear. And as already mentioned a few times, it should be as light as possible. And all these things together are right now not not available on the market from the state-of-the-art robotic systems. Because of that, we used our own control architecture. So a behavior-based architecture, and I think Professor Vance already introduced it in his presentation. So I will just shortly explain it with a short example. And this example is the behavior network for the rollover prevention. So we start in an unsafe mode where the robot is not allowed to drive because the default setup is that we have not met the requirements, which is to be in the pitch and roll threshold. That means we have an area where the robot is able to drive if he is in between the angle of inclination. That means, for example, between 0 and 45 degrees. And if we are in this area, and for example, for the pitch threshold, we get a signal that we are safe. So we unlock the safe mode, and we are allowed to control the velocity. And with the controlling velocity, we are able to drive. And if the value if the value which we are actually in the robot is changing and the pitch threshold is no longer valid, we get in the unsafe mode. We are not able to control velocity anymore. The vehicle itself won't drive. And because of that, the vehicle will stop. And with this kind of architecture, we can safely control the robot also in this terrain. And now I will talk about the optimization ideas. As you have seen in the first picture of our mock-up, we have built it out of aluminum. This robot is and steel. This robot is comparable heavy, and the idea is to reduce the mass. We want to use additive manufacturing approach. For example, build up like in this picture. This robot should also be modular, so that we can also make applications like mulch, trim, or defoliate. And the idea is that to use a modular concept, so that we have a base frame which is really very compact and has just the most necessary stuff inside, like batteries, industrial PC, and just these 4 wheels. And then we should have hitches to add the different attachments. There are more or less 3 different approaches of hitches. These also already known 3-point hitch. This is very common in agriculture. And here's a top-mount attachment, which has this T form and is extendable in height and width to get the attachments near the foliage wall, and also here for connecting easy trailer or something. Yeah, these are different attachments for ground cultivation, cultivating like mowers, flail mulcher, and the cultivator itself could also be possible, but with this you should enter in the ground, and therefore you need very high forces, and this is not possible with our lightweight construction. And yeah, the idea is to use such a mower, flail mulcher, which in a lightweight construction. And yeah, these are also some other use cases. We could use different attachments like defoliator and the trimmer. here's the problem that the center of gravity of these attachments is very high. As you see here, this is a height of 2 meters, which makes the robot very unstable. And because of that, this is more or less very different to attach. And here is also carrying device, which could be used in harvest for transport the grapes uphill. Yeah, the spraying tower is a very lightweight construction, which we already used, or we used another kind of it. And yes, this now I jumped too far. This are the different applications. No, nevertheless. And yeah, this is the future work which has to be done from our side. And yes, thank you for your attention, and I'm now opening for questions.
I have a question. So, what is now from the control side is possible? What type of control this robot itself has? Because I can see you can pull the robot with the rope.
With a winch, yeah.
Yeah, and what else is the control?
Yeah, the idea of the control is that we are able to recognize the surrounding and just to drive uphill and downhill. And yeah, and then
can you turn a little bit, or is there
just adapt, because in general you know that the that the rows are really straight.
Yeah.
And because of that, you have just to make little adaptations, yeah, that you come uphill, because there's no need to turn. And because of that, and this with the known environment is a more or less easy way for just driving. But the next step, of course, would be to then adapt attachments. For example, go down and mow or something. But at this point, we are right now not really. But yeah, this, I think the combination of both will get more difficult.
The sensor system that you showed for the perception, there are ZEDs, yeah, and I think some other laser scanner was there also.
Yeah, and in the first test there were laser scanner.
So what exactly is the purpose of that? Are they for detecting the crops, the wineries, and then yeah, you showed also the tank in the start. So also the purpose of this is to precisely spray, detecting the where.
Yeah, for example, this how to come out of this presentation?
No.
No. Now I can just jump to this. Yeah. Here, this idea was to make a rough estimation of the. I don't know if it's possible to see here. You see the vines at the vine, and here the grapes. The idea was that you can recognize every vine and can more or less make a note and bundle here the information to it. For example, a calculation of the yield, or application of spraying.
So the application could be yield. Also, you can predict the yield, how much is it coming, and also the monitoring the health. Also, maybe
this is also an idea, but in this special case, you have the problem if you can recognize, for example, of RGB pictures, the injured leaf, you are too late, then you can't do anything like this. And but also an idea is that you can bound informations to this recognized.
Maybe another idea could be you can also use the multispectral here. Yeah. Attach something and see what type of data that it can give, because it has the much more information and other bands that are there.
Yeah,
you guys also already have it, so attaching it and maybe check it for the health monitoring maybe. And for example, you find out, okay, this area or this field, this row is has disease or not accordingly, then you can spray or whatever fertilizer or pesticide needs to be sprayed on, you can then do it.
This
Later on. This can also be
this is
one
a good idea.
information that I can think of.
This is a good idea. Yes. Yeah, and of course, this application of spraying agent is also a use case that you see there is no foliage at all. There has not to be a spraying agent because there are in Germany right now new regulations of application of spraying agent. Some spraying agents are no longer allowed to use, and because of that, you have to be careful with the use of the.
Or maybe this precise spraying of water, maybe, or whatever, or giving the water.
Yeah, exactly. This is also.
Anyway, there is rain all the time in there in Germany, but sometimes it's not. Then maybe.
Yeah, exactly. Okay, thank you.